Hey guys, my name is Patrick,
And my name is Tom.
and we're going to be going over blackbody radiation in this video. So I'm going to go ahead and start with an example of a project that we did over the summer, me, Tom, and your teacher Tegan. So we used this machine you see here in the image to compress a sample and heat it up really hot. And so as you can see inside that chamber there, the object is glowing orangish red. And the reason it's doing that is, again, because it's really hot. But why do objects glow when they become really hot? Like, what is going on? What are the physics behind that? And so we'll go ahead and get into that a little bit later. But right now, I'm going to give a little introduction, talk about the electromagnetic spectrum and the energy of light and that sort of thing. So let's talk about light. So light, it behaves as a wave, and we've known that for quite some time now. It is composed of two components. One is an electric field component. So the electric field propagates out as a wave. We'll use this as our electric field wave. And then the second component is a magnetic field component, and that one propagates in the same direction but perpendicular to the electric field wave. And so those waves propagate together through space and time and perpendicular to each other. And so this is a generic light wave, but there are many light waves and they all have different wavelengths. So now let's take a look at a generic wave. And I'll talk about the wavelength of a generic wave. So if we have a wave here, and this is kind of an uneven wave, but if we have a wave, the wavelength is just the distance from peak to peak of the waves. And we use the wavelength to calculate the energy for a light wave. And the energy of a light wave is given by this relationship here. So here we have energy is equal to hc over lambda. Now what the heck are h and c? I already told you what lambda is. Lambda is the wavelength, but h and c might not be known. You guys might know what it is, but let me go ahead and just let you know what it is in case you don't. So h is Planck's constant, which is roughly equal to 6.63 times 10 to the negative 34 joule seconds. And c is the speed of light, which is 3 times 10 to the 8th meters per second. Okay, so as I mentioned, there's many different types of light, and those different types have different wavelengths. So, as you might have guessed from that equation, and I'll write it again here for you, if they have different wavelengths, then the different types of light also has different energy. And the wavelengths of light are usually represented on a wavelength spectrum. So here let's draw the spectrum out, or at least a rough approximation of it, where wavelength increases from left to right, and from the equation above you can see that energy is inversely related to wavelength. So as we increase wavelength, the energy decreases. So over here, where wavelength is really small, we have really energetic waves like gamma rays, and X-rays, and UV. And so all of these light waves are on the left-hand side of the spectrum, the more energetic waves, are not visible to our naked eye, but they are definitely still there. We can perceive them in many different ways, just we can't see them. But as we move farther down the line to longer wavelengths, we move into the visible spectrum of the wavelength spectrum, where we have our blue light and our violet light, and then we have our green light and our yellow light and our orange light, and then all the way over to the very far side, on the very far right side, we have our red light. And so all of these light waves, or this region of the spectrum, is visible to our naked eye, and that's everything we see. So as we move farther down the line, as the wavelengths get larger, we move out of our visible range again. And so the very next part of the spectrum is the infrared spectrum. And then farther down the line we have short waves, and then long waves, and longer waves. And so infrared rays are important because this is the type of light that is mainly shined or mainly emitted by a black body that we would typically see in everyday life. So now let's take a look at an example of a black body that is emitting infrared radiation. So as I mentioned in the last slide, there is many different types of light that we cannot see, but yet it's still there. And I ended the last slide talking about infrared radiation. And so I'm going to use the example of night vision or infrared goggles. Now let's imagine we're all sitting in a room together and it was pitch black. We wouldn't be able to see each other because our bodies would not be reflecting the light that is shined down upon us, because there would be no light to reflect. But our bodies would still be emitting light, and that's because our bodies would be behaving as black bodies. And the light that our bodies would emit would be infrared light. And this is how infrared goggles or night vision goggles work. They perceive, or they can see, the infrared light that's emitted by your body. So you can see here in the object, the guy is illuminated in yellow and orange and red, and that's because he's producing infrared light. And the night vision camera or the goggles or whatever they have focused on him is able to see that light. Okay, so now that I've spoken with you about light and the light spectrum and all the different types of light, as well as the energy that the light carries with it, I'm going to go ahead and pass it off to Tom to really explain what a black body is, because I've mentioned black body a few times now, but we really haven't talked about what it is. And then he's going to go ahead and explain why and how a black body emits light radiation when it gets hot.
Alright, so I'm going to be talking with you guys about a little bit about black bodies, what they are, black body radiation, and some of the theories behind it. So, to describe a black body, we can think of a black box, and this black box is having electromagnetic rays interact with it. Now, a black body, a perfect black body, would absorb all of these energies and then re-emit them, not reflect them. So it would absorb all the energy and then re-emit all the energy. Now that is not found anywhere in our universe, but most black objects have this same kind of characteristic. So that black body could be thought of as a solid material, so it's made up of atoms. And now we know that atoms have different orbitals of electrons that are surrounding it. And when an incident ray of light interacts with that atom, it promotes electrons to become more energetic. So then the more energetic electron will want to go back down to its original energy state. And once it goes back down to its original energy state, it will re-emit energy in the form of a photon. And that energy of the photon will be the difference in energy between the two energy levels. And as the energy level difference becomes greater, the emitted photon will begin to have greater energies as well. And you can visualize this as you put more energy into your black body, the black body will then begin to emit higher energies of light. So when you see a material that's glowing red, and since red is a high wavelength type of light, the energy associated with that wavelength will be low. But as you keep increasing the energy of the system, of the black body, the light will then become more intense, the photons will have more energy, and then begin to go through the spectrum. So you would see first it glow red, then yellow, then orange, and then you could get all the way to blue if you increase the energy to a point where it would be emitting that low wavelength of light, which has a high energy. Alright, and the last thing that I'd like to go over with you guys is the intensity versus wavelength graph. Now this graph is very important to understanding how black bodies irradiate different wavelengths of light, because this graph shows with temperature where the maximum wavelength is for that temperature. Now this line would show a emission of high temperature, while this one would show an emission for a medium temperature, and this one would show an emission for a low temperature. Now as you can see, the peaks for these three lines all are showing different values for wavelength. And this is very important because the visible spectrum is around these two lines. This is visible light. This would be infrared. And this would be ultraviolet and X-ray. And this shows with temperature how the emission of light from black bodies can go from the visible light to the infrared light, but also can go above visible light into the ultraviolet and X-ray. And that is all we are going to talk about with you today. Thank you for watching, and we hope you learned something. Bye-bye.